All right, for this video, we're going to be discussing energy, work, and metabolism. Okay, so we're going to start to develop the tools necessary to understand the set of biochemical reactions that occur within a cell that supports life. And so by the time you're done with this video, I want you to be able to define the term energy. I want you to talk about the different types of work that a cell must do. Describe the first law and the second law of thermodynamics as it applies to chemical reactions. I want you to be able to describe what the difference is between anabolism and catabolism. These are the two forms of metabolism. And what must one know about a reaction to determine if it is spontaneous, if it will run in the forward direction as written? And finally, to use reaction coordinate diagrams to differentiate between exergonic reactions, endergonic reactions, and reactions that are at equilibrium. Okay, so first, energy can be defined as the capacity to do work, the capacity to cause change, the ability to move matter against opposing forces. And what I should say is we don't really ever measure energy directly. We look to see what has been done, what work has been done, what change has been caused, what matter has been moved, and we backtrack. If this is the work that was done, then this is the amount of energy that we must have seen, that we must have used. So it's kind of an indirect measurement. Now, energy can be used to do work. Now, what is the type of work that we can see within a cell? Well, we can see chemical work. We can see the work necessary to drive, to convert an endergonic reaction into an exergonic reaction. So normally, taking 6 CO2, taking 6 water, slapping them together to make glucose, normally that's an endergonic reaction, but the cell uses solar energy to convert that reaction into a spontaneous reaction. This will be really important for today, for this video, and the next video I'll talk about. Another form of work is active transport. So moving molecules against their concentration gradient requires energy to do that work. Physical movement, moving things along, for example, moving this motor protein along this microtubule, that mechanical movement requires work, and therefore that's work that requires energy. So, chemical work, transport work, mechanical work are all types of cellular work that require energy. Now, there's two types of energy. The first is potential energy. It's the energy of position, water behind a dam. It's not doing anything yet. There's a ton of energy there, but it's not doing anything yet. For the purposes of this class here, chemical energy, the energy inherent in the bonds of complex molecules such as glucose. Now that energy isn't doing anything yet, but we can start to break down those bonds of that hold those atoms together, releasing energy and then using that to do work. And then, of course, there's the kinetic energy, the energy of motion. So this water rushing down from high concentration to low concentration, spinning these rotors here and the turbine, and thereby generating electricity. A thermal heat is a form of kinetic energy. Unfortunately, life can't use the energy of heat. All right. So let's talk about the rules that guide the transformation of energy. Okay? The transformation from one state to another state. This is called thermodynamics. And we're going to look at this in the context of a reaction. Okay, so here we have our reactants. Now the reactants are always the left side of a reaction. That's what defines the term reactant. But the product is always the right side of the reaction. Okay, so that's super important to understand when we start to look at the equation necessary for delta G. Okay, reactants on the left side, products on the right side. Now, notice if we make up some value for energy, so 50, this is totally make-believe, but I'm just giving you an arbitrary unit of energy. Our reactants have 50 energy, and the products have 40 energy. And so this reaction has occurred, and notice our products here have less energy than the reactants. Now, the first law of thermodynamics says, hey, we started with 50 units of energy, we ended with 40, we have to have the same, the amount of energy we started with has to be equal to the amount of energy that we ended with. That is the first law of thermodynamics, which means that we've got to account for 10 units of energy. Well, that energy was released. It was released as energy that can be used to do some sort of work. Okay, so we call this, any reaction will always, all reactions proceed with the release of energy. They always proceed from high energy to low energy, and then that difference is the energy that has been used or can be used to do work. That's the first law of thermodynamics. You can't lose energy. You can't just disappear into nowhere. You got to be able to account for it. So if our products are lower energy than our reactants, that difference has to be accounted by energy that's been released to use to do work. Now, here's a question. Can this 10 units of energy be used to convert those products back into those reactants? Basically, what I'm asking you is, can you make a sort of an infinite loop here where reactants are turned into products, the 10 units of energy that's been released to do work goes back into the products to convert the reactants, convert back into reactants, which then are broken down into products. The 10 energy used to do work is used to convert those products back into reactants. So that is what the next law of thermodynamics tells us. It answers this question. Can that energy that we've released in the reaction, can it be used to just keep going over and over and over again? And the answer is no, because the second law of thermodynamics states that with each transfer from one form, reactants, to another form, products, there is a certain amount of energy that is released that is unusable. It's heat energy. So what happens here is when our reactants, becomes products, right? So we have to account for 10 units of energy. Well, it turns out that a couple units of energy are released as heat, and they're gone. We can't use them for anything. So the only usable energy we get out of that is about, in this particular case, is 8 units of energy that can go on and do work. And notice, that's not enough to convert these products back into reactants. So the answer to this question here is no. We cannot use the energy from this reaction to then run it backwards again, because not all of those 10 units of energy here are going to be available to us. Some of it is going to be unavailable as used heat energy. So every time you convert one source of energy, reactants, into another source of energy, products, you lose a little bit of energy as heat. So we can't have a system in place of this continual loop, because every round of that loop we lose a little bit of energy as heat, lose a little bit of energy as heat, lose a little bit of energy as heat. Okay. Now that we understand that, we can start to understand how reactions run. Well, reactions are only going to run towards greater stability. They're only going to run with a release of energy. So if we take a look at reactants and we take a look at the products, as long as the products are a more stable state, that they are at a lower energy state, we know our reactants are going to become product. We know that this reaction is going to proceed. Okay, so let's word this in another way. A reaction always runs from a high energy to a low energy state. A reaction always runs from a less stable to a more stable state. A reaction always runs in the direction in which energy has been released that can be used to do work. Right? This is a really important concept to understand. Now that we have an idea of the nature of chemical reactions here, and we'll go into more detail in a little bit, but let's take a look at metabolic pathways. Right? These are the sets of biochemical reactions necessary for life, and we can break them down into two types. There are anabolic pathways. These are the biosynthetic pathways. These are the pathways in which the cell must invest energy into in the form of ATP and NADH, NADPH, FADH2. These are electron carriers. These are high energy models that we're going into a lot more detail later on, where you're investing the use of them to take low energy molecules and convert them into high energy molecules like proteins and polysaccharides and lipids and nucleic acids. We're storing energy in these large, complex molecules. These are biosynthetic pathways. They require sources of energy to be able to run. The opposite is catabolic pathways. These are the pathways where where the opposite is occurring, that we are taking high energy molecules like carbohydrates and fats and proteins. We're breaking them down into their constituent low energy monomers and components, and in so doing releasing energy that we are storing back into our ATP, back into our NADH, our NADPH, FADH2. So these are breakdown pathways, breaking down large molecules that release energy that is then stored in chemical bonds. So in this case, cellular respiration, turning glucose into energy that is then going to be stored in those molecules into CO2 and water. Whereas our anabolic pathways was using the energy of the sun to organize and convert CO2 and H2O into glucose. They're opposites of each other. Okay. Now, to take a look at these biochemical reactions that are occurring in both anabolism and catabolism, that are occurring in metabolism, to define endergonic versus exergonic reactions, we need to look at a unit called Gibbs free energy. So all reactants, all products have some inherent energy involved. And so we call that the G of the reactants, the energy of the reactants. We call that the G of the products, the energy of the products. And so ultimately, when we're defining G, when we're describing G, we want to use G to tell us whether a reaction, as we're looking at it from the left to right in the forward direction, okay, so the default direction of the reaction is left to right. That's the forward direction. Is this reaction, as written, is it spontaneous? Will it proceed? Will reactant become product? Well, what we need to do, remember, reactions always run towards the lower energy. So if we know that the G of the product is lower than the G of the reactant, we know this reaction will run. So we make ourselves a little equation. We call that the delta G, and the delta G is the difference of the energy of the products minus the energy of the reactants. So what that tells us is if the products are lower energy than the reactants, our delta G should be negative. Right? If our product's energy is lower than our reactant's energy, then the delta G, as written here, is going to be negative, and that means a reaction is going to run, and we call that an exergonic reaction. So let's take a look. This is called a reaction coordinate diagram, and on the y-axis it tells us our free energy. So here's the free energy of our reactants, way up here. Here's the free energy of our products, way down here. We know that reactions run from high energy to low energy. Beautiful. So this reaction, as written, is exergonic. Reactants will become products and energy will be released. Okay, how much energy? Right here, the difference between the two. That is the amount of energy that's going to be released that can be used to do work. Now, let's take a look at the opposite. Here's our reactants, okay, and here's the energy of our products. So we have a situation here where we have more energy in our products than we do reactants. So our delta G, products minus reactants, is actually going to be a positive delta G. We call this sort of reaction an endergonic reaction. And as written from left to right, it does not run. However, that doesn't mean nothing is going to happen. What that means is if you pop those reactants and those products into a little microcentrifuge tube or a beaker and you say, okay, let's let it run. Well, what's going to happen is the reaction is actually going to run in the reverse. Product is going to be broken down into reactants. So energy is going to be released, but it's going to be released as the reaction runs in the opposite direction as written, in the reverse direction. So endergonic reactions have a positive delta G. And what that means is in the forward direction, it doesn't run. Okay, but in the reverse direction, it does. It will run in the reverse direction with a release of energy as products become reactants. And finally, what happens in this case? What happens in the case when the energy of the products is equal to the energy of the reactants? Is it going to run in the forward direction? No. Right? There's no difference in energy. Is it going to run in the reverse direction? No. Again, no difference in energy. More accurately, what I should say is that for every molecule of reactant that breaks down into a product, there's going to be a molecule of product that breaks down into reactant. And so the net effect here is that there is no production of reactants or products. We have reached in this reaction equilibrium. And so let me again define that. The equilibrium is the point at which the energy of the products is equal to the energy of the reactants. And I should say it's the energy of the products, the energy of the reactants, not the concentrations of them. That's important to understand. So at this point, we have a delta G of 0. So make sure, and you go over each one of these examples, look at them carefully, be able to identify and the difference between exergonic and endergonic and reactions in equilibrium. Make sure you understand that when I write out an equation like this, a reaction, that by definition, everything on the left side of the reaction is reactants and everything on the right side of the reaction is products. Really important to understand. Okay, so again, review these learning objectives and make sure that you understand and can do each one of those points.